how it ends on the right. The great thing about degree 2 and degree 4 is that indirectly tells you how it ends on the left as well, right? Because degree 2s are parabolas. You guys talked about this a lot. It's quadratic. The arrows are both up or the arrows are both down. Yeah? Degree 4 is the same. It makes either a W because it gets you an extra little bump or an M, but they're either down or up, right? So with degree 1, 3, and 5, the leading coefficient told us how it ended on the right, and because it was 1, 3, and 5, it ended the opposite on the left. Yeah? But degree 2 and 4 are even degrees, so how they end on the right, they end on the left. Arrows in the same direction, right? And what is this? This is the constant. What does it give me? Sorry, what did you say? Y-intercept. Because y-intercept x equals 0, correct? And if I put x in for this term and x into this term, they cancel off and I'm left with c. We agree? So that's why the constant is always the y-intercept. All right. So that didn't change, even though this is degree 2. Still tells you how it ends on the right, the leading coefficient, and still the constant, right? Degree 2 didn't make a difference on that spectrum, other than the fact that the left is in the same direction. What are the maximum number of x-intercepts for this one? 2. Why? That's right, but why? The degree is 2. Yep. So the maximum number of x-intercepts is always equal to the degree, whether it's 1, 2, 3, 4, or 5, same reasoning, right? Degree 1, 3, and 5 had a minimum of 1 x-intercept. Because your end behavior of your graphs are always in opposite directions, it's going to have to cross somewhere. We agree? Okay. However, degree 2 and degree 4 have arrows in the same direction. So what is your minimum number of x-intercepts? 0. Because it could be completely above or completely below, correct? Like, for example, that. Now remember, once we get the minimum number of x-intercepts and the maximum number of x-intercepts, we can have the varying number of x-intercepts between that. So if I know it's 0, and I know the max is 2, that means I can get everything that falls in between, which is just a 1, right? So that would be 0 x-intercepts. 1 would be when you have a tangent. So I actually have 1 x-intercept. I technically have 2, but they're the exact same thing, right? So that's that multiplicity 2 we were talking about. Or I could have 2 totally different ones, right? So this is 0, 1, and 2. So you can always get the varying levels in between. What is your domain of these graphs? X and out of the real, so it goes on for life, right? Out to the left and out to the right, it's concave up, or out to the right and out to the left, it's concave down. So it goes on for life. Every polynomial, so degree 1, 2, 3, 4, 5, or any more, but we stop at 5 because that's the curriculum, it doesn't have to do. They're always XER. Because their arms are both going up, still out for life, or they just go, it's still out for life. Correct? So unless it's a word problem, because word problems could involve like time, for example, and time has to start at 0, time can't start at negative whatever, right? Then your domain would be restricted. But it's not a word problem. Every polynomial's domain is x and m in the reals, or negative infinity, positive infinity. The range, however, is not YER because the arrows are not in opposite directions. So if I had one that looks like this, this is a what? A vertex, and specifically a minimum, yeah? Okay? If I say that this is at, let's say this is, I'm going to take that minimum off from being there because that looks stupid. So if I say that this is D, the value of D, we'll say negative D. Okay? Is my range, my Y's, range, Y's, same thing, right? Greater than negative D, the rest of the graph, or is it less than negative D? Greater, because the graph's above it, correct? Is it equal to or not equal to D? It's equal to, because your minimum is actually negative D, right? So my range is going to be greater than that, right? I'm going upwards. So it's going to be Y such that Y is greater than or equal to negative D YER. Now it needs to make sense to you, or else you're trying to memorize if it's equal to or not. You shouldn't be memorizing if it's equal to or not. When you found the minimum, you got negative D, correct? So it's equal to that or higher. Yeah? I know people struggle with doing interval notation sometimes when it's inequalities. So if this is negative d is right here, it's going to be a closed dot because it's equal to, and then it's greater than it. So it would head towards this arrow. We agree? What does this arrow represent? Infinity. And then you literally just put a comma in between. Square bracket because it's equal to negative d, round bracket because it's never equal to infinity. So this in set notation would just be square bracket, negative d, comma, infinity, round bracket. It's literally just representing a number line. Okay? So you have to be in the order of the number line. Does that make sense? I could also have a graph that's concave down. It's like this. This is a what this time? Maximum. And we'll say that this is t. Well, now the entire graph is what t? Less than. Or equal to. So it would be y such that y is less than or equal to t. Y is the sum of the reals. If I drew my number line, I put t on it, it's equal to it, so I put a closed dot. It's less than, so it goes this way. What does this arrow represent? Negative infinity. Last 8. So infinity can never be equal to, so you put a round bracket. T is equal to. So my interval notation would be negative infinity t. You need to know both of them because they can ask for any of the two. Okay? So that's quadratic, degree 2. What's the last one we have to go over? Degree 4. We've done 1, 3, 5. We've done 2. Now we have to do 4. Okay? So degree 4 is called quartic. So they're linear, quadratic, cubic, quartic, quintic. So it's ax4, and then I just keep going till I run out of variables. Plus bx cubed, plus cx squared, plus dx, plus e. Now quartics either look like a W, they could look like a really nice W, or they could look like an M, but the M could be like kind of wonky. It could be like that. Still an M, correct? What would this one have? What type of leading coefficient? And what would this one have? And they're in the same direction, so we know it's an even degree, right? So this would have a negative, that's a lie, positive leading coefficient. So technically A would be greater than 0 for that graph. We agree? If this was my equation. And this one we would have a negative leading coefficient. So A would be less than 0. This is how it ends on right. Now some people, I'll give you ones like with a bracket. So for example, I might give you, don't write this, let's say I gave you y equals 3, x plus 2 squared, and then negative 2x plus 1. And people will tell me, okay, it ends up on the right. Is that a leading coefficient? Do I have an x beside it? Is there brackets involved in this? This is factor notation, right? This is factored form. You can't use the same rules. It's only for standard form that it does that. Because if I expand this out, I have 3, x plus 2, x plus 2, negative 2x plus 1. If I expand this out, it would be 3 times 1, x times 1x times negative 2x, and it would actually be negative 6x cubed. So this is actually a negative leading coefficient. It would end down. So you can't go based off of just that number sitting in front. Does that make sense? You have to actually expand it out. All right, that's just a caveat. Don't worry about that. Okay. What is the maximum number of x-intercepts? 4, because it's equal to the what? Degree. What is the minimum number of x-intercepts? Pardon? 0. Because it's an even degree, arrows are in the same direction. It could be completely above, or it could be completely below, right? Never touch the x-axis. You have a crazy W completely above the x-axis, right? And then the varying levels I could have is 0 all the way to 4. So I could have 0, 1, 2, 3, 4. Like this one over here, right here, has 2. This one has 4. Like I could have all the varying levels in between, right? All right. Say this is your graph. And this is negative m. What's my domain? X and out of the reals. It's polynomial, not a word problem. It doesn't change. Arrows going out to the left and the right. What's my range? Y such that y is greater than or equal to negative m. Y, yeah. Now some people get confused because they're like, well, this is a minimum too. Cool, but the graph goes lower than that. So the graph involves every value from negative m upwards, correct? Technically. Watch yourself when you find minimums. You guys will sometimes grab the x and say it's greater than or equal to, like say the x on this one was 2. You'll say, oh, it's greater than or equal to 2. No, it's not. That's the x. We have to find the y of the minimum, right? Because we're doing range. Range is always y's. Yes? So watch yourself on that. And then it's greater than or equal to negative m. So we go square bracket negative m to infinity. And then if I had a graph like this little tick here is negative c. What would this one be? Domain is still XCR. What's the range? Y such that y is what? Go down to infinity. Less than or equal to negative c. And if I'm less than, I'm from negative infinity to that value. Square bracket is equal to. I taught the unit circle in grade 11 at the time. It's overwhelming to get people to truly understand it. So we kind of just go through, we show you guys what it is, and then we call it a day. Okay? So what we're going to do is try and understand this. Did you know that this unit circle is actually between negative 1 and 1, negative 1 and 1 on a graph piece of paper? Did you also know that this here is the origin? So right here is 0, 0. Okay? And then we have, so what this is if I take a piece of graph paper and I zoom in, bless you, on the 4 first boxes. So this would be your y-axis, this would be your x-axis, this would be 1, this would be 1, this would be negative 1, this would be negative 1, correct? And like your graph paper could keep going. Yes? Like, right? The graph paper keep going. This is like a zoomed in really tiny spot on a piece of graph paper. Yes? Your unit circle is here. On those 4 little circles. And by circles I mean squares. On the 4 little squares, that is your unit circle. So your unit circle, if you drew it on graph paper, would be like twice the size of the end of my pen here. If you drew it on a piece of graph paper, right, it would just be that little tiny circle, right? Locking in those 4 little boxes around 0, 0. Yes? And then we just blow it up. So it's on your page in front of you. It looks huge, and people think it's way bigger. But really what that is a little circle between negative 1, 1, negative 1, 1 on your graph paper. You know what I'm saying? So it's really tiny, actually. And we just expand it and blow it up for you. Okay? So, going back to this. what we're going to do is we are going to actually fill in the degrees first, and then we're going to envision that on a Cartesian plane. So we always start off with 0 degrees on the x-axis. Okay? Then we're going to talk about reference angles this year. Reference angles are the angle between the x-axis and the terminating arc. So from here to here, what is that angle? This is 30 degrees, correct? Okay. Let's fill in all the blue ones first. I should have done that. So this is 0. Then this is what? This straight up and down one. 90. And then this straight across one. 180. And you guys used to have those compasses where you went around, or tractors, and you would draw them. Okay, and we'd have 180. Then this would be 270. And this would be, another one could be here, of 360. We agree? So let's go back to our reference angles. Go away. So if this is 30 here, yes? Then this is also what? 30, correct? So we'd go 180 minus 30 and we would get 150. Then this is also what? 30, so we go 180 plus 30 and we get 210. And then this is 30, so we go 360 minus 30 and we get 330. Fun fact, those 4 degrees will come up with the exact same coordinates, just some being positive or negative because it's on a Cartesian plane. Right? So those red ones will come out with the same answers. Okay, let's go to the next one. So, from here to here is what type of reference angle? 45 degrees. Now that reference angle is going to stay the same on this whole Cartesian plane. So this here to here is 45 as well, correct? So how am I going to get that degrees? 180 minus 45, which is 135. Then I'm going to do 45 again to here. So I'm going to go 180 plus 45 and get 225. And then it's 45 from here to here as well. So 360 minus 45, which is 315. Okay. What's our last reference angle in the unit circle? 60. So then from here to here is also 60. So how do I get that angle? 180 minus 60, which is 120. And then I do 180 plus 60, which is 240. And then I do 360 minus 60, which is 300. This you agree with, right? Okay, I told you that this is on a Cartesian plane. It's from -1 to 1, -1 to 1. We agree? So I could technically, I'm just going to show you here, I could technically go like this. And that would be a box, right? On the unit circle, your very first, it would be a box on a piece of graph paper. That would be the left box, left bottom box. Yeah? Okay. So we're going to go through and do all the coordinates of the blue ones first because they should be easy. So I know that the unit circle has a radius of 1. So this from here to here is 1. So what is this coordinate? 1 and 0. Okay? Then what's this one going to be with a radius of 1? 0 and 1. And then this one will be -1 and 0. And then this one, 0 and -1. Now the rest people try and memorize, like 3, 2, 1, 3, 2, 1, over 2, which way do I go, where do I do it? But remember that your answers, everyone paying attention, your answers that you have a choice for are 1/2, √2/2, and √3/2. That's what the rest of the coordinates are going to be. Yes? In some variation. That's what we're going to fill into all the rest of the blanks. 1/2, root 2 over 2, and root 3 over 2. Before we actually talk about those, though, let's go and actually put in our signs of all of our coordinates. So in quadrant 1, what are all of our coordinates? Positive, positive. So do I need any signs? No. In quadrant 2, what are our signs for our coordinates? Negative, positive. So I'm going to put some negatives in there. Right? In quadrant 3, what are they? Negative, negative. And in quadrant 4, our x's are positive, our y's are negative. Okay. So we filled in our signs so we don't mess those up. So I want you to give me what these are as decimals. So what's 1/2 as a decimal? 0.5. So that's half the radius. We agree? Because the radius is 1. So that's half the distance. Yeah. Okay, root 2 divided by 2. Type it in your calculator. Give me a decimal. 0.707. And then root 3 over 2? 3 divided by 2? Yes. So technically, if this is the radius of the unit circle, let's pretend it goes around in a circle, yes? 1/2 would fall about here, right? I don't know what else. And then 0.707 could be like here. And then 0.8660 could be like here. We agree? Kind of like distances on that number line, on that 0 to 1. We agree? Okay. Let's go back to our unit circle. I know that I need to fill it in for those things. I know that the 45, the actual distance from here to here, because I'm finding a coordinate, this is a coordinate, correct? On that Cartesian plane from 1 to -1, it's just a coordinate. Do you see it? It has the same distance x and the same distance y. Do you see? From here to here, the same distance as from here to here. Our x and y's are the exact same distance. Yes? So every 45 is actually root 2 over 2. Root 2 over 2. Because their x and y values are the same. They're 0.707. So I go to this 45-degree reference angle, and I go root 2 over 2. I don't have to worry about the signs because I've already put those in. I go to this 45, and this coordinate is going to be at 707x and 0.707y. Negative 0.707 because it's in the quadrant 3, and negative 0.707 as well because they're in quadrant 3. Because I am legitimately stating this coordinate on a Cartesian plane. That's what you're doing. Yes? And then I have to state this coordinate on a Cartesian plane. Well, it's going to be positive root 2 over 2 because it's a positive x in quadrant 4, and negative root 2 over 2 because it's a negative 1. Do we agree? Okay, most people are really good at those. And then it's like, I don't know which one's half from root 3 over 2, so I'm just going to memorize. 1, 2, 3, 3, 2, 1. I don't want memorizing. I want you to understand why the heck you're picking what you're picking. So I know that this coordinate needs to be 1/2 and 0.866, or a 0.866 and 1/2. Those are my options. Yes? So let's actually look at the coordinate itself. Here's the coordinate. Is my x at 1/2 of 1? Or does it look like perhaps it's at 0.866 because the blue was at 0.707? It's at the 0.866, right? So my x for this one is root 3 over 2. Now what is my y? 1/2. That's half the distance from 0 to 1, isn't it? Is that not a distance of 0.5? Yeah. And it's going to stay the same if I take this one. It's going to be at 1/2. I kind of went downhill there. But anyways, it's going to be at 0.866, but negative. So negative root 3 over 2 because of where it's located. And then the y distance is 1/2. Wow, I really drew that downwards. Ignore that. Instead of 1/2. Positive 1/2. Then this one is at negative 0.866, so negative root 3 over 2, and negative a half. And then this one's at positive root 3 over 0.866, root 3 over 2, and negative a half. Right? And we know the 60s flip. The reason why the 60s flip is because it's a 30, 60, 90 triangle that makes up those things. It's your teacher taught you last year. 30, 60, 90 triangle that makes them up. So here, this is a 30, here's a 60, here's my 90, right? But when I go to the 60 degree one, which I don't remember what color I picked up. When I go to the 60 degree triangle one, this is my 60, and then this is my 30, correct? So the triangle flips. So you're going to get different x's and y's because the triangle flipped. One was 60, one was 90. But if you forget that, who cares? Follow this down. I'm trying to find the coordinate to here. My x is what? What way between 0 and 1? It's about half. Do you agree? And what's my y? 0.866, because this was 0.707, remember? So that's why they flip. You see that? That triangle flipping. You had a flatter triangle, now you have a much more vertical triangle. Half root 3 over 2 for this one. And then this is going to be negative a half because it took me over to here. And then negative root 3 over 2. And then this is a half. And negative 3 over 2. So we know how to fill it in, but do we know what the heck it even tells us? Fun fact, this unit circle will give you trig ratios without your calculator. So put cos of 30 degrees. Make sure you're in degree mode. Go to mode and put in degree mode. You're going to be flip-flopping between degree and radians in grade 12. So there's no such thing as like, put it in degree mode and never touch it. So make sure you're calculating degree mode and go cos of 30. Is that what I said before? 0.866. 0.866. Blah, 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 blah. Agree? Okay, cool. That's an answer. Is that an exact value or is that a decimal? It's non-terminating, non-repeating, not exact value decimal, right? Cool. When I go to 30, guys, which one of those is root 3 over 2? X. Correct? That's why your teacher told you last year that each of these coordinates actually represents a trig ratio, a cos trig ratio and a sine trig ratio. Calgary Stampede. Cos theta, sine theta. So if I put in cos of 30, I should be getting the x, root 3 over 2. Yeah? Put in cos of 150. Type it in. What's the answer? Negative 0.8660. If I go to cos of 150, that's negative root 3 over 2. Same answer, is it not? That's the exact value of it. Do we agree? Okay, cool. I want you to do sine of, let's do 210. Sine of 210. It won't be 0.5. It'll be negative 0.5. Because if I go to sine of 210, it's the y. It's negative a half. Correct? So could I get every exact value in reference angles of 30, 45, 60, and 90 for sines and coses right off my unit circle and not have to touch my calculator? Yeah? Can you run test points on your unit circle to see if it's right? Yeah, you could go cos of 225, see if it matches, right? You could do sine, whatever, and you can check your entire unit circle if you really want it. Now, that is what this unit circle is for. It's to give us exact values of those specific reference angles. But what about cos of 22? Put that in. Cos 22 is a crazy decimal, right? Okay, let's think about it. If I went on this unit circle, people are like, well, cos 22 is not on here. So if it's not for 30, 45, 60, or 90, I can't ask for an exact value. Exact values come off this unit circle, right? For 3 over 2, half. Yeah, we agree? But I can still ask you for cos of 22, because cos of 22 is on this unit circle. Do you see how this unit circle is actually like connected? Do you see how that's a connected line is just a whole lot of coordinates, right? If I drew an infinite number of coordinates, they would be on top of each other and they would make a connected line, would they not? That's what a line is. It's just a whole bunch of coordinates connected. We agree? So if I go to 22, this is 30. This would be half of 30, which would be like 15. If I go to like 22, let's pretend it's here. It's not the most accurate thing I've ever seen, but okay, it's there. If I follow that down, because I want cos is x, is it not? So I want cos of 22. I could also have sine of 22, and that would make this coordinate, wouldn't it? Do we agree? What is cos of 22? What's that on your calculator? 0.927. 0.927. Well, this red one was 0.866, so does that seem kind of realistic? Yeah? Okay, what about sine of 22? Put it in. I'm expecting it to be less than 0.5 just because of where it's drawn, correct? What is it? 0.374. So can you give me every degree a cos and a sine on the unit circle? Can you give me a coordinate on the unit circle? You would just do cos of that angle, sine of that angle, and you get a coordinate on the unit circle, yes? True statement? I just can't ask for exact values if it's not 30, 45, 60, and 90, but I can ask for it. Like I could ask for the unit circle, I could ask for the coordinate on the unit circle at 126 degrees. You tell me. Coordinate on the unit circle, 126 degrees. Coordinate. Coordinate is an x and a y, we agree? The most simple way I could write this coordinate is to say cos of 126 degrees will get me my x, and sine of 126 degrees will get me my y. True? It's the most simplest way I could do it. But they might ask for it as a decimal. So what's cos of 126? Why is it negative? 90's here, 180's here, 126 somewhere in there. What's in quadrant 2? X is negative, y is positive, right? So I know my cos is going to come out as a negative. I know my sine is going to come out as a, and what is it? 809, blah, blah, blah. Right? Does that make sense? Your unit circle just gives you sine and cos trig ratios, which then indirectly gives you tan trig ratios, because tan is sine divided by cos, which also gives you the 3 secondary trig ratios we're going to talk about this year, which are secant, cosecant, and cotan, which is just the other 3 flipped. They're just reciprocal trig identities. So if you know cos, you know secant. It's just reciprocal of it. If you know sine, you know cosecant. It's just a flip of it. If you know tan, you know cotan. It's just a flip of it. So finding those 3 secondary trig ratios are not the hard part. If you know the 3 primaries, you know the secondaries because they're just the reciprocal of them. That's it. Nothing crazy. People overthink things. And if you understand trigonometry, if you understand chapter 4, you have 4, 5, and 6, if you understand chapter 4, 5, and 6 are not bad. And honestly, chapter 4 is not even that bad. If you understand what the unit circle is and what you're getting from it. It's not just this circle that you fill in really fast. It gives you information. Okay? Does that make sense? All right. So for the rest of the class, I'm going to hand out the polynomial handed. It is due on Tuesday. The catch on the polynomial handed is number 6 and number 7 have to be done on a separate sheet of paper and stapled to the back of the notebook. Number 1, you might want to do on a separate sheet of paper because it's factoring. You have to factor algebraically. Some people have squished it, whatever you can squish. I don't really care. I would never want to do that. I would want to have it easy. So you can have 1, 6, and 7 on a separate sheet. You'll staple it to the very back of the booklet. Okay? You get the rest of the class as long as you're working.